Right. Welcome back to CE3007. Today is 19 January 2022, Wednesday. We are now on week 2 of the SEM 2 of 2021-2022. Today I will answer tutorial 1, question 1 to 4. And after this, I will put it in the YouTube channel. If you have any questions, do put it in the chat and I'll try to answer them. In this question 1a, we are asked to determine the period of a discrete sinusoid. Basically, we are interested to find that if you are given xn, when is this equals to xn plus, I'll use the word p here, and p is non-zero, and p is integer. So we are basically trying to find when does the signal xn repeats when, of course, in our case, n is integer. So here n, then the sign here means belongs to, and here is the set of integer values. Right. So we are given the first signal. The first signal is a cosine with amplitude A, and we have this expression inside the cosine. So typically, if you remember continuous time, xt equals to some a cos 2 pi f t plus phi. And we know that it is periodic across, for example, x of t plus capital T, which is a cosine 2 pi f, and here's small t plus capital T, and then plus phi. And if we can find the capital T, which is the period, then it is repeating. In the continuous time case, t is real number, and capital T is a real number. So we can always find the period. Right. However, in discrete time, you must be very careful because sometimes the signal is not periodic, even though it is a cosine or a sine. So what are we interested in? Well, the idea is this. We write the equation. We can ignore the constant a because that's useless. So basically what we want to find is when is this equals to, let me find a space for you. So cosine, when is cosine theta equals to cosine theta? And that happens when this is true, 4 pi, and so on and so forth. So equivalently, it is cosine theta plus 2 pi times k, where k is an integer value. So once we understand that cosine repeats every 2 pi, then what we are left with is this cosine. Our question is pi over 6n plus pi over 3. When is this equals to cosine pi over 6n plus pi over 3 plus 2 pi, right? Now, the thing is that is changing is that little n here. We want to find when this pi over 6 small n plus big N, well, big N is the period, or I call it P in this example. When is this equals to pi over 6n plus 2 pi k? Okay, and k can be 1, 2, even -1, -2, up to you, any integer value. And once that is true, then we can solve. So when you go through the calculations, basically you'll realize that we can do it this way. We'll ignore the phase because that's useless. And we work it out, and the answer is p equals to 12. It means that x of n is always equals to x of n plus 12 for any n. So we can find the period. Now I'm going to I'm not interested in, of course, this is also equals to x of n plus 24, because if this is the smallest period, then any multiple of the period is also repeating. But we are interested in the smallest period for any quiz. Now, let's plot this guy. Cosine pi over 6n. What does it look like? And why is it equals to cosine pi over 6n plus 12? That's what we're claiming, right? Now, remember what does this equation mean for this value of pi over 6n? It means that for every step that I take, for every n from 0 to 1 or 1 to 2, pi over 6 is included into the equation. So we are moving by pi over 6. What is pi over 6? Pi over 6 is 2 pi over 12. 2 pi is 360 degrees, right? If you guys prefer to think of it as degrees, 12 is this 12. Therefore, it is actually 30 degrees. So the equation cosine pi over 6n is a discrete time that for every step it takes, it will move by 30 degrees. Where did we see this? We see this in the tutorial or in the lectures. Let's see the lecture notes. In our 02A signals.pdf, page 23, go to look at this figure. This is a cosine, and each step that I take is 30 degrees. So this is basically 1 cosine pi over 6n, and then I'm plotting this for various n. Where is the number 12? Look, it is periodic. You count. Step 0 times n 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And at the 12 point, it repeats. So we can see where the 12 is from this graph. So n x of 0 is equals to x of 12, is equals to x of 24, equals to x of 36, and so on. So now you can see the figure of a cosine pi over 6, as well as now understand the idea of finding the period for this first question. Okay, so here we end for the first question, Q1A. I'll pause now to take questions. Now, this is question 1B. We are given another equation, x2 of n, in this case is a sine now, and remember it is like sine of omega n, and omega is the digital angular frequency, and it has a radian per sample unit, and n is sample, and therefore what we have is radian per sample multiplied by sample. What comes out of this expression is radian. Okay, and then this radian, the angle is sent to sine, and therefore we get the value. How we want to understand omega is this. I'll repeat again. It is that each step, as I move from n to n plus 1 to n plus 2, at each step, when I move, I'm moving by omega, whatever omega is. In this question, I'm moving by 1.8 pi radian. Now remember, when we move by 2 pi radian for a sinusoid, we're moving one complete cycle. So moving 1.8 pi radian at each step is very close to moving through one complete cycle. All right, now this is very strange. So I will suggest that you go to Vitaly's video to understand what's happening here. Now, let us solve for this signal, whether this signal is periodic or not. So In here, again, if we begin, sine of theta is equals to sine of theta plus 2 pi is equals to sine of theta plus 2 pi k. So it doesn't matter what k is. K can be 1, 2, 3. And in this example, you'll realize that k is not 1. All right. So let's try. Let me shut these teams down first. It's very, in this particular example, you realize that it's very strange because we're trying to find this expression 1.8 pi small n plus p, where p is the period in integer and is equivalent to this guy. So that basically we are getting this equation. Sine of theta is equals to sine of theta plus 2 pi k, where theta is the original expression of 1.8 pi by n. Now, if you work it out, you realize something is very strange. It is that, well, let's work it out. We have 1.8 pi n plus 1.8 pi p is equals to 1.8 pi n plus 2 pi k. So this guy goes away and we are left with 1.8 pi p equals to 2 pi k. We can throw away the pi and therefore we get p is equals to 2k over 1.8. Now, this is a very strange thing because you think that, well, we know that we need p to be integer. And then if you substitute k is equals to 1, it wouldn't make sense because it's 2 divided by 1.8. So what is the smallest k that we can find? And k must also be integer because k is the number of cycle. What is the number of k, right, that we should do to get p to be integer? And it works out to be k equals to 9 and p equals to 10 samples. What it means is that this sequence repeats itself every 10 samples. X of n is equals to x of n plus 10. Okay, and then, but when you plot it out, it's very strange because what's happening is that every sample that you take is almost close to one cycle. After 10 samples, you are actually going across 9 cycles. All right, so later on, we'll show you a figure. Now, let me pause now. Now, in question 1C, is now it's even more strange, okay, than the previous question. Again, you think that it is nothing but xn equals to sine of omega n. And now omega is simply 0.5, right? What's wrong with that? That means every step, n from n to n plus 1, we are moving by 0.5 radian. It seems that there is nothing wrong with this equation. And because it's sine, you would think that it is periodic, but it is not. And let us see why. Because what we need to do is to get this guy 0.5 n plus p to be equals to 0.5 n plus 2 pi k, right? Now, you realize that if you work out the math, then what happened is that this wouldn't happen. And the reason why this wouldn't happen is because this guy cancels. 0.5 p is equals to 2 pi k. Therefore, p is equals to, then you realize, oh, it's 4 pi k. What's wrong with 4 pi k? Well, p needs to be integer. K is an integer. Any integer. 4 pi k is an irrational number due to pi being irrational number. So p can never be an integer. So in this case, our friend, this very simple looking, innocent looking equation does not repeat. Okay, and why is this so? All right, you go and plot. So you look at here, it looks like a sine wave. The red line looks like a sine wave. every step that I make, I am moving by 0.5 radian, 0.5 radian. Okay, every step that I make, I'm moving by 0.5 radian. Now, does it repeat? And you say, yes, of course it repeats. But actually, no, it doesn't repeat because you will never look at the top point. It is never matching. Okay, it doesn't repeat. There is no sequence that you can find such that xn equals to xn plus p. There is no p that you can find, okay, for this innocent looking sequence. All right. Okay, I'll pause now. So this is the tutorial 1, question 1D. This is the solution. In the solution, you realize that I am using the stem plot. This figure is the stem plot. You need to draw stem plot when I ask you to. Do not draw for me the plot graph. The plot graph is a line interpolating between the points. Okay, remember we are in discrete time sequence. Things between the points, the time index n and n plus 1 are not there, which is, it looks like this. Okay, so in this, the red lines at different time index shows you where the values exist. Between the time index, no value exists. Okay, so this is what we are asking for. So I want you to draw for me this, guys. All right. Remember that the idea is that nothing exists between this point here. Okay, nothing here. All right. Only values exist in every time index. Okay. All right. So that's question 1D and E. Now let us see question 1E. Question 1E is a very interesting question. Let's see the question first. In question 1E, I'm given CT, a continuous time signal, and I'm asking you to plot from t equals to -10 to 10. And I'm also given, I'm asking you to plot for me y dt, omega n, and these two things looks identical. Of course, the only difference is that t is continuous and n is integer. However, you know that when you try to plot time for continuous, it will never make sense. How can you write a program to plot from time -10 to 10? Then you say, why not? And the reason is for continuous time, t can be 0, 0.000, I mean 1, 0.000, whatever, how many decimal point you want. It is impossible to write and plot a function like that in a program. So the best we can do is actually we say that as we are plotting from -10 to 10 seconds, we are plotting in steps of 1/1000. Now, therefore, actually, everything that you do in a computer program, you'll never be able to draw up for infinite time at infinite precision. What you can only do is to plot it at discrete time anyway. However, we fool ourselves. When we plot with very, very fine precision, we see a curve. So this is what we see. Right. So in the bottom, the green guy actually is the curve, and I'm plotting from -10 to 10, and each point I'm plotting is very, very close to each other. That is why you see a curve. Okay, so now I'm going to show you the code. The green guy is the continuous time signal, and the red guy is the discrete time signal. Let us see. So now I'm going to do question 1E for you. And then I run, and that is the answer, the green guy and the red guy. Let's look at the code. Question 1E. Now, I say start time is -10, end time is -10. Let's zoom in -1 to 2. Okay, and I'm going to replot this from -1 to 2. So from -1 to 2, the green guy is the continuous time signal. So you see that I'm plotting start time, end time at 1/100, 1,000. Right, I'm now going to, instead of this, I'm going to plot the green guy with 10 points in between. Okay, so let's see. Now, okay, I'm going to plot the green guy, only 10 points in between. So you see that actually the green guy is still, well, it's sampled at 10 times in 1 second, or, well, yes. So what happened is that as I increase the number of points for my green guy, it becomes smoother and smoother. And if I increase up to 1,000, so basically the green guy now forms like a continuous line. What about the red guy? The red guy is the discrete time signal I'm doing from n equals to minus, in this example, -1 to 2, but instead of index 1, that means -1, 0, and 1. Nothing in between. Okay? So that is the difference between the green guy, which is a continuous time signal, because I'm allowed to go to any point in time and plot a value, while the red guy is a discrete time signal. I'm only allowed to plot at every integer index, n equals to 0, 1, 2, -1, -2. So that is the difference. Now, let me now extend the plot from let's say -3 to +3. And we are now going to zoom out to look at this. You realize that the green guy is moving up and down very, very quickly, but the red guy is only sampling, in between the green guys. And now if I extend it even further, -10 to 10, you realize that, well, let me get this thing up. You realize that it appears that the discrete time signal is a very slow cosine wave, while the green guy is a very fast sinusoid. So this is the idea of aliasing. When the actual signal is moving very fast and we are sampling not fast enough, it appears to us that the original sinusoid is of a low frequency. And this is what's happening. Okay, so this is question 1E, showing us the difference between, actually, you realize that omega is the same, 1.8 pi, but they behave very differently. All right. I'll pause recording now and take questions. Now, what's the difference between continuous time signal and discrete time signal? Right. I think I made a mistake here. This should be T. Okay. For continuous time signal, the x-axis is time in seconds and is real. For discrete time signal, the x-axis is in integer, and integer meaning that n equals to -infinity to infinity, but n can only be integer. All right. Now, the unit for omega is radian per second. And of course, the unit for time is in second. And radian per second times second will get radian back. And radian is being sent to, of course, the sign, and everything is fine again. So that's the idea. What about this guy? This is in sample index 1, 2, 3, and omega is radian per sample. Small omega has a name. It is digital angular frequency. Means at every step, I'm making how many radian per sample. Okay. The other guy is every second, how many radian? Radian per second. All right. So this is the difference between big omega and small omega. Now, please be careful about big omega and small omega. In certain books, big omega represents discrete time. In Oppenheim, big omega represents the angular frequency for continuous time. Small omega represents the angular frequency for discrete time. Okay, so that's the difference. The notations of big omega and small omega is not universal. All right. Now I'm done with question 1. Almost? Oh no. I have one more questions here. So let's see the question first. And in the last question, I have an equation, 3 cosine omega n plus phi. And I want to express this as a cosine omega n plus b sine omega n. So what's the cool idea about this? This is a sinusoid with frequency omega, small omega. It has a phase shift. It has an amplitude. What about this guy? This guy is also a sinusoid. It's a cosine with frequency omega. It is a sine with frequency omega. So these two frequencies are the same. They are omega. The amplitudes are different, A and B. What we are saying here is this. The very cool idea of this is we can express a cosine or a sine with different phase shift, different amplitude into the sum of cosine with the same frequency and the sine of the same frequency. And in fact, Fourier series is doing this, or Fourier decomposition. It will decompose a cosine wave into it will decompose the cosine wave with phase shift into a cosine wave without phase shift plus a sine wave without phase shift. All right, that's the cool idea. Okay, let's try. So now we have 3 cosine, I think, was it pi over n? Oh, here. So this is actually 3 cosine pi over 6n plus phase shift of pi over 3. And we want to find is equals to what value of, let's say, b cosine pi over 6n plus c cosine, sine, yeah, pi over 6n. So that's the question. Decompose the original equation into sum of cosine and sine without phase shift, but existing in the same frequency. So the question is find B and find C. All right. So this is a math question. How to tackle this? The simplest idea is this. We use the trigonometric identity and we see, say, a cosine can be decomposed into this expression. So what is this expression? Cosine pi over 6n. This is for theta 1. And the phase shift is plus pi over 3. This is theta 2. Now we substitute this. So this is cosine pi over 6n times cosine of pi over 3. The other guy is sine of pi over 6n, sine of pi over 3. So now we can know how to compute B and C. Please remember there is a minus sign here, and then this is our answer. Okay. So go through the math, and then you see that this is how I find my answer. So this is the C, this is the B, and how do I prove to myself that it works? Well, so for sanity check, let us now plot for a sequence from -20 to 50, and then I will create two Y's. The first Y based on the original expression, where the amplitude is 3. This is pi over 6n plus the phase shift, which is pi over 3. And then A is calculated as cosine of pi over 3. B is calculated as sine of pi over 3. Remember the C in front, okay, guys? Please don't drop it. Now, the second equation is the A times this guy. That means the cosine at pi over 6n. The B is multiplied by sine of pi over 6n. Remember the -1 here. So we plot y0 and y1. Y0 is the original expression, which is the red line, and y1 is the green line. Actually, when I draw this, I shouldn't be drawing this. I should. So I'm going to now change my code and show you how I would have drawn it instead. So this is my code for question 1G. So let's run the code first. So you'll see that the red point lands on the red line. But I'm just going to show you question 1G. I want instead to show you mine plus. Okay, so I shouldn't be showing you the red line. I should, because remember, I am only what do you call it? I am only generating four discrete time sequence. So you can't see, that's a problem, right? You can't see the red line. So that's why I put a minus here to draw the red line. And now you can see the red line going up and down, and the green points lands exactly on the red line. Maybe if I put X, you can see. Yes, so you can see X. Now if I use, what about 0? Now you can see X landing on 0. Yes, correct. Okay, so you can see the X landing on the red dots. So showing us that the two equations generated identical results. Of course, this is just a sanity check, but the math tells you that it's the same. Okay, so I'll pause now. Right, now let's continue with question 2 and 3 of tutorial 1. Question 2 asks us to find the energy of a signal, and question 3 asks us to find the power of a signal. Energy and power of a signal. So in the solutions, please go to look at the definitions first. The definitions is in this slide. What is energy? Energy is nothing but asking you to, for discrete time, okay? So this is discrete time. Take all the samples, square the samples, and sum it, the energy. So the energy is basically taking all your samples, squared, and then sum the values. That's for discrete time. For continuous time, energy is defined like this. Take the absolute value and square for each time. And then you integrate for all time because we are in continuous time. For digital signal processing, because our interest is on the digital sequence, we are only interested in the discrete time energy formula. Now you have to be very careful with this. I'll give you an example. So if I draw for you this signal, so basically it is a signal that goes from n equals to -infinity to infinity, and it has an amplitude value of 1. Okay. So what is the energy of this signal? And then you realize that the energy is infinite. Okay, the energy is infinite. Right. So this, if the energy is infinite, it is not an energy signal because we say that it is an energy signal if it's only E, yeah, the energy equation is less than infinity. All right, so this is the definition. So sometimes we ask you, is this sequence an energy signal? And if this is true, then it is an energy signal. All right, what about a power signal? A power signal is, it looks exactly the same, right? Here, n will go to infinity, but we are dividing by the period, okay? So 1 over 2n plus 1 is nothing but the period, because if we are going from minus n to capital N, we are taking 2n plus 1 points. So we are basically taking the energy divided by how many samples, but we are of course taking it across all time. Now, so if this p infinity is less than, it can be computed, it is not infinity, and each is greater than 0, then it is a power signal. So this is the definition of an energy signal and a power signal. So some interesting observation. So a signal can be energy, can be power, or neither. Okay, so it can be one of them. However, it cannot be both, yeah, at the same time, an energy and a power. All right, because here is greater than 0. All right, so now let us see our question. The energy of this signal. We are given this sequence. Let's see the sequence. The sequence is this. Xn equals to 2 to the power of minus n for n equals to greater equals to 0, 0 otherwise. So let's draw this sequence first. It is the Xn equals to 2 to the power minus n for n greater equals to 0, equals to 0 otherwise. Means if this is a sequence, this is 0, minus 1, minus 2, and n. The first value at here is 0, 0. So everything on the left-hand side of time index, our sequence is 0. What about at time index n equals to 0? 2 to the power minus 0 is actually 1. 2 to the power 0 is 1. What about index 1? 2 to the power minus 1 is half. What about index 2? 2 to the power minus 2 is 1/4. And so on. So we have that sequence. The first one is 1 for time index 0, half, 1/4, 1/8, and so on. So this is the line that I'm drawing. So this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. Right. So we have this sequence. And we want to find the energy of x of n. So remember, energy is energy equals to summation n equals to negative infinity to infinity. X of n square. So I'm going to square my sequence first. So I take my blue line and I square them. So my blue line, 1, the first value is 1. 1 square is 1. Second value is half, right? Half square is equals to 1/4. Where's 1/4? This guy. What about this guy? 1/4, actually it was 1/4, and square, 1/16, this guy, and so on and so forth. So now you see that to answer this question, I have to generate the original sequence, and then I have to square the sequence, and then I have to sum it. So what you realize is that I am summing 1/4 to the power of n for n equals to 0 to infinity to get the energy. Now, this expression will be familiar to you. This is the geometric progression. So you remember the equation, and this equation is, when we have this expression, you will reduce to this guy if r is less than 1. Okay? And what is our r? Our r is this guy, 1/4, and therefore we get this. So please remember your first year math as we do geometric progression, and this is the answer. The energy of an infinite sequence, so this is the infinite sequence here that we are summing, interestingly, is not infinite. It is 4/3. Now, a long time ago, I always ask the student, right? If the first value I give you is 1, and the second value I give you is 0.1, and the third value I give you is 0.01, and the fourth value I give you is 0.01, and I give you all the infinite, what is your sum? And of course, the sum is. So it took, you have to figure it out. It's very strange, right? I'm giving you values, but yet when you sum infinite amount of them, the sum doesn't explode. And the reason is because every time I give you a new value, it is so much smaller that it doesn't, change the number at all. So this is one way of thinking why infinite series does not explode. As long as the next value I give you is smaller than, a certain, it doesn't affect the whole sum, then you can do an infinite series and it doesn't explode. Okay. All right, that's the idea of the energy. Okay, any questions, guys? Now we are in question 3. Now, unit step. So let's be clear about u of t versus u of n. Here, the unit step is with respect to real. Here, it is with respect to the integer z. I'm going to draw continuous time in seconds, and u of t basically means this. This is a red line here, go up and then go up. And at this point in time is 0. And this value is 1. This whole thing is u of t. Now, I'm going to ask you, guys, what happened at time 0? Because there is a discontinuity, right? So at time 0, is it value 0 or value 1? So if I want to be very, very precise, I'll draw a point here, and I'll draw a circle here. So this is in your calculus. And if I draw a circle here, means at time 0, it is 1. This is an open circle, means at time 0, it is, you will stop here. At time 0, there's only one value, which is 1. Okay. So maybe I should draw it this way. Then you can draw it this way. Open interval, close interval, and there's nothing in between here. Okay. And this is time. And this is value 1. And this is value 0. And this is u of t. All right. So this is unit step for continuous time. So now, let us find the power of the signal. Okay. The energy of this signal is infinite, right? You sum 0 here and you sum 1 here. And of course, when you sum 1 to infinity, it's infinity. But the power is not infinite. Why? Because the power have that thing in the bottom to divide. Right, let's try. We are going to sum this guy now. So I should not be drawing this. I should be drawing only at integer points. And I should draw it as a stem plot, for example. And then now the blue points doesn't exist. And now I'm asking you for n equals to -1, -2 until infinity, 0, 1, 2, 3. I have to square the value, but I'm squaring 1. So it doesn't matter. Now, this is the powers equation, which is the energy divided by time. So we begin with minus k to k here first, and we are going to send the limit of k to infinity. But let's pretend that k is not infinity first. All right, then in the bottom is 2k plus 1, because if we are summing from minus k to k, we are taking 2k plus 1 point. That's the idea. Now, because we know that the unit step happens only for time k, for time n greater equals to 0, therefore I'm only playing with n equals to 0 to k, changing my limits. Right, I'm summing the value for squared it, and the value for each step is 1. So 1 square is still 1. Now, then, of course, you say, I reached this point, and it will not make sense if I set k to be infinity. However, we do this trick in calculus where what do we do? Well, we assume that k is not infinity first. So on the top is k plus 1, right? Because we are interested in k plus 1 point. So on top is k plus 1. Bottom, we have 2k plus 1. We divided the top and bottom by k. So we bring the k out and we can cancel them. Now, this allows us to set the limit from k to infinity. So these guys disappear. And the answer is the energy is half. So this is very intuitive, because although the energy goes to infinite, but if I'm dividing it by the period, and the period is also infinite in here, well, this guy is some energy, the other side got no energy, so power is half if we assume that the period is infinite. Okay, I think that's it. I will leave question 4 for the next